design of welded joint eccentric loading. So there are three cases for eccentric loading. We'll be taking all these one by one. So first case is the eccentric loading, that is in plane load. So here in this in plane load we have these two plates 1 and 2. They are connected through welded joint, this C type welded joint, and a load F is applied in the plane of weld geometry at a distance E from the CG of weld geometry. So here it is important to explain that whenever we are designing any component, we have to find out the effect of load on that component. So here in this case we are designing weld, so that is why we will be seeing what is the effect of this load on the weld. So for this we will first find out the CG of the weld geometry or weld group, and then we shift this load F to this point CG, to this point G, and then we can find out what is the effect of the load on the weld. The same procedure we have done in eccentrically loaded riveted joint and bolted joint. In all these cases, all those cases, we shift the load to the CG of bolt geometry, and then we find what is the effect of that load. So let us redraw this weld represented through lines like this, just enlarge portion, and let us divide this in three sections. This is 1, this is 2, and this is 3, and the effect of this load F after transferring to the CG is load F and a couple F into E. This load F will induce in plane shear stress as given by this load by area. Here A is the area of total weld group or weld geometry, and this F into E is the moment acting in the plane of geometry, so that is why it will induce twisting moment, and the twisting moment will induce secondary shear stresses, and these shear stresses are like this. So this is torsion equation, generally used for circular component only, but we are assuming here that this is also applicable for non-circular component. So that is why with this assumption we are using this equation, where J is the second polar moment of area about an axis which is perpendicular to axis and YY passing through G. So that is how this IXX plus IYY will give us J, and IXX, and this once J is obtained, we can find out the maximum value of tau S, and maximum value for constant value of J and Fe will be obtained at a point where R is maximum, where R is the distance of point from this CG. Let us consider these 4 points where the distances are likely to be maximum, and we can see clearly that distance is maximum at 1 and point 2. And at point 1 the primary stress is this, secondary stress is this, which is perpendicular to this position vector R1. We can find out resultant of these two stresses using parallelogram formula, and now once to find out this value tau maximum, no doubt we must know what is the value of tau P and what is the value of tau S, and tau S is obtained for if we know what is the value of J. So here in such cases the most important thing is to find out the value of J. Here are the stresses shown on each point set, point number 2, 3 and 4. So our aim is now to find out value of J, and we know that value of J it depends on the value of IXX and IYY. and this Ixx and Iyy we can find only if we know where is the location of this CG. So first of all we have to find out the location of CG, then we find out value of Ixx and Iyy, then it will give us value of J. So value this centroid, we obtain centroid using this equation, these formula, expanded form for this particular case, as we have 3 sections, so that is why this is there, where A1 is area of section 1, A2 is area of section 2, and X1 is the distance of CG of section number 1 from the reference axis. So here for X we have X bar we have this as reference axis, and for Y bar we have this as reference axis. We are measuring the distances from this axis and this axis. So once X bar and Y bar are obtained, we can go for this J calculation. So Ixx is given by I1xx, I2xx and I3xx, where I1xx is the second moment of area of section 1 about xx axis, I2xx is second moment of area of this section number 2 about xx, and I3xx is second moment of area of section number 3 about this axis xx. Similarly for yy, now we can find out the values of I1xx, I2xx and I3xx. I1xx we obtained by parallel axis theorem, because we know the second moment of area of section 1 about its own neutral axis passing through the CG in this case. So this is I1x1 is the second moment of area of section 1 about its neutral axis, and this is to be transferred to xx using parallel axis theorem. So that is why A1 d1y square, where d1y is the distance between the two axes passing through the CG of section 1 and axis where we want to shift this I, and I1xx is 1 by 12 L1 into T cube, and this area L1 into T in d1y square. Similarly we can find out A2xx. A2xx is the second moment of area of section number 2 about this axis, so that is equal to A1xx. A3xx is the second moment of area of third axis. Here the x, its own axis, and the axis about which we have to transfer this, both are coinciding, so there is no parallel axis theorem is required. And just see the expression, this T is the equivalent to width here and L2 is equivalent to depth, so that is why it is TL2 cube. Similarly we can now we can write down substitute here in this equation, we get this expression, and this is equivalent to this, because if we can neglect this TQ term, which is very small as compared to these two terms, so this Ixx can be written as equivalent to this. So for neglecting the parameters or the terms, we have to see what are the terms which are in higher order in T. So those terms we will be neglecting, other terms we will be keeping intact, the term which will have T only as linear, no power. Similarly we can find out A1yy. A1yy is nothing but it is the second moment of area of this total geometry about yy axis. This is obtained using the second moment of area of section 1 about its own yy axis, and then transferring it to the yy axis of the geometry this and this both will be same, and here in this case for section number 3 its own y axis is this, so we have to shift it using parallel axis theorem. So in this case all three sections will be shifted for getting final value, and then we can neglect the t cube terms to get final value of Iyy. So this is how we can find out Iyy and Ixx. That will give you value of j. So we can also we will be also needing theta for calculating resultant of tau primary and tau secondary. So this is how theta is obtained. This is given by, if this angle is theta, then this is y bar divided by L1 minus x. So this is this total is x1, and as those total is L1, and from here to here it is x bar. So this is L1 minus x bar. So this is how we can find out theta, and then we can calculate tau maximum. The another eccentric loading case is out of plane load. This for example, we have taken this value, this example, that one particular member is attached to a wall using these two welds. So here if again the method will be same, that F we have to transfer here to the CG of the weld geometry. Weld geometry can be located easily, it is symmetrical section, so that is why it will be midpoint between this and this. So J is this, we are shifting F here to this G, so load F will be there and F into E will be acting here. So this F into E is basically acting in XY plane like this. If we can see it here, this is in XY plane, and here the plane which we are showing is YZ plane. So we cannot show it here like this. We have shown with the another symbol that we use for the showing moment, that is double arrow. So this double arrow in direction indicate that this moment is acting along z axis. So from here if we use our right hand rule, we can find out the direction of this moment is along negative z axis. So thumb direction will give us the direction of moment. So that is why it is shown here if we consider this as positive and this as positive. So again this F will induce primary shear stress, and F into E that will induce bending stresses on the weld. So this is how we can find out this sigma and tau, and no doubt this it means that at any point now we have biaxial state of stress, that one is tau and another is sigma, and this for sigma will be needing value of I. So here we will be using IZZ because we have to find out value of I about this ZZ, because ZZ would be the neutral axis in this case for this weld group. So we can find out this IZZ, the sum of these two as shown here, and this value as we have done in our previous case, this 1 by 12 LT cube plus this area, and this we are shifting it from this to this using parallel axis theorem. So we can neglect this term, and only value that we will get is this. So as we have discussed that this is biaxial state of stress, so whenever there is biaxial state of stress we have to make use of theories of failure. So here we can make use of shear stress theory, maximum shear stress theory, and then we can find out whatever is desired. So this is the theory that we have to use, and if we use maximum principal stress theory, this would be our design equation. The another kind of load is in plane axial load. What is the meaning of in plane axial load? That is clear from this figure. So here let us have this type of a angle which is having this much length, and that angle we want to fix on any wall using welding. So in this case the load, we assume that we are applying this load axially, that is axially is along the axis, centroidal axis of the member which we are welding. So this is the member that we are welding. So this is L-shaped member. So first of all, to find out the location of this load, axial load F, we have to locate the CG of this cross section through which we are applying load F. So this is the primary condition, that in this case we apply load along axial direction, and axial direction is that axis is passing through the CG along the length of the member. So here this F is passing through the CG, and that no doubt is along the length of the member, so that is why it is axial load. And we try to apply load F through this G, so that there is no unbalanced moment on the weld. Basically we are reducing the stresses on the weld by applying the force F through the CG, that we'll see. So to analyze this type of weld, we can find out how much for this load, how much total length is required if we know what is the thickness or what is the weld leg, maximum weld leg that we can use in this case. So that total weld length we can apply on the one side, we can apply on the other side, or we can distribute equally, or we can distribute like this, L1 here and L2 here. So how to find out these length and what proportion we should distribute the total length, that is the important part of this type of analysis. So if I draw a free body diagram of this member that we have welded, so this force F will be balanced by this F1 and F2. These are the forces that this weld will apply on the member. So if we draw the weld, then these are the forces acting on the weld, equal and opposite to this. This will be equal to the resisting stresses, and this stress multiplied by area will be equal to F1. So from here it is clear that we have this type of forces acting on weld and the member. We have to design weld, so we have to consider this F1 here and F2 here for this weld, and for F1 for this weld. So this these forces, they are in plane shear force, so that is why it will induce in plane shear stresses. Very simple. Now we can find out this F is equal to F1 plus F2, and the moment F1 into Y1 and F2 into Y2, they will be same, because if we take moment about CG. So if there is if this F is not passing through CG, then we will be having some unbalanced moment at CG, and that moment will induce bending stresses on the weld. So that is why we always try to apply load through the CG of this geometry. So now we can write down, this is how we can find out the total length, and once the total length is obtained, we can distribute these length like this. F1 and F2, they are given by this, so F is sigma 1, and just see we have replaced sigma 1 by tau d and sigma 2 also by tau d. It means we try that the maximum amount of stress induced in this weld and this weld should be same. Otherwise one weld will be overstrengthened and another weld will be weaker, and we are just wasting the weld unnecessarily. So that is why we use this expression, and such that when we apply load in both the weld, same amount of stress should be induced. So using these two equation and this equation, we can find out how much L1 and L2 is required. Here this is the these expressions we can use directly for calculating I and G, but I personally feel we should not use these equations, because sometimes it may not be available. These formula may not be available in examination, or you may confuse with some expression. It's better to use basic principle of calculating IXX and IYY and J for the problems. Thank you for watching this video, and if you like, please share.